This is the final project presentation for CS2316 for Group 124. Our topic was health and fitness data. We wanted to learn about the correlations between location, fitness, incomes, and many other factors with health and obesity. And we selected our data sets because they provide publicly available information about health behaviors and outcomes across the U.S. Our data sets are a CSV from the CDC website with obesity percentages by location. Second, we have a Harvard website with a table containing calories burned per exercise depending on a person's body weight. And third, we have a JSON file containing health metrics for counties across the U.S. In Phase 2, we started with the CDC CSV. Before the shown section, pandas and NumPy are imported and the CSV is read. This section identifies unneeded columns and drops them, then replaces unknown values with nans. Then it converts income ranges to statistically significant integer values. Finally, it splits geolocation into separate longitude and latitude, and a clean file is created after the shown code. And this is the result. Secondly, we have our Harvard web scrape. Imports are made, the HTML is read, the first table on the website is used, and the header row is fixed. The data is converted to integers, and unknown data is replaced with nans, and a clean CSV file is created. And this is the result. Lastly, we have our JSON county data. Imports are made and the URL is saved prior to the shown code. The shown code requests the data, converts it to a Python dictionary, then extracts column names and uses them to build a data frame. It drops unneeded columns and converts column names to snake case for consistency. Fills missing data with nans, converts columns with number data to be numeric, and renames columns so it's clear what they represent. After this shown code block, the clean data is saved to a clean file. This is the resulting table. In Phase 3, we talked about insights and visuals. Our first insight concerns the CDC CSV file. In this code, pandas is imported and the CDC clean nutrition file is read. Then data is grouped by year, and averages for 3 years and year over year are computed. These are the results. The lowest average year was 2012 and the highest was 2023. The year-over-year percent change shows the relative change in obesity rates, and the most significant change is 20% increase from 2022 to 2023. It is also clear that there's been an upward trend of obesity rates since 2019. Insight 2 uses linear regression. The x value is median income and the y value is obesity rate. The model uses standard 75% training, 25% testing model. The coefficient shows that for every $1 increase in median income, the obesity rate decreases by 0.000015%. The mean squared error being so high indicates that the correlation between obesity and income is not very significant.
Now moving into Insight 3, we started by looking at long-term obesity trends across states, and we imported the clean CDC dataset and grouped the data by state and by year to calculate each state's average obesity percentage annually. From there, we ran a simple linear regression for each state to measure how quickly obesity rates have been rising over time. We made sure to exclude states that didn't have enough yearly data to make the trend meaningful. This allowed us to create a ranking of the top 10 states with the fastest increasing obesity percentages. Here we can see the results, where states like Tennessee, North Dakota, Alabama, and Indiana showed the steepest upward trends. What's important here is that the increases vary a lot by state, meaning the national averages don't tell the full story. This insight highlights that obesity is rising more quickly in certain regions, especially in parts of the South and Midwest. This helped us understand where obesity growth is happening the fastest, which connects to the later insights about activity levels and health risk. For Insight 4, we focused on physical inactivity, obesity, and calorie burn data. We imported the nutrition dataset, the physical inactivity dataset, and the Harvard calorie burn dataset. And we identified a walking-related activity and calculated how many calories per minute it burns. Then, we grouped every state into one of the 5 major U.S. regions and calculated average obesity and inactivity for each region. Using those averages, we estimated how many extra calories each region accumulates per day compared to the lowest risk region. Last, we converted those extra calories into the number of walking minutes needed per day to offset this difference. Here are the results, and regions like the Southeast and Southwest need the most daily walking to counteract their combined obesity and inactivity levels. On the other hand, the Northeast requires the least, which matches what we see in national health trends. This insight shows how lifestyle and health behaviors differ across regions and how these differences translate into actual physical activity needs. Insight 5 brings together everything from our previous data sets and adds location data. We used obesity, inactivity, and the geolocation with latitude and longitude to create a combined risk score. We then used the risk score to divide the states into 3 categories: the low, medium, and high risk. To capture more complex patterns, we generated polynomial features and created a logistic regression model to classify each state into one of the 3 categories. Finally, we calculated the probability that each state belongs in the high-risk category. The model reveals which states are most likely to fall into the high-risk category, and as expected, many southern states show extremely high predicted probabilities. One useful aspect of this model is that it doesn't only identify the most obvious high-risk states, it also spots those in the middle range that might be emerging risk areas. Overall, this shows the value of using logistic regression to reveal nonlinear health patterns. The first visualization gives us a simple box plot of obesity percentages across all states. It highlights the variation and helps us quickly identify states that fall outside of the typical range. This directly supports Insight 1 by giving a clear picture of how spread out the obesity values are. Visualization 2 uses the probabilities from Insight 5 to create a choropleth map of the United States. The code abbreviates state names so that they are displayed better, and then it drops rows without a valid state code. Each state is shaded based on how likely it is to belong to the high-risk category, and it's based on activity level, current obesity percentage, and geographic location. This makes the regional patterns extremely clear, particularly the concentration of high-risk states in the South, and it's a very helpful visual summary of our classification model. Visualization 3 uses the Harvard dataset to show calories burned per hour by activity and body weight category. It shows that heavier individuals burn more calories, and it also highlights how different activities vary dramatically in intensity. High-intensity exercises burn far more calories regardless of weight, while low-intensity activities produce much lower calorie expenditure. This adds helpful context to the walking-based predictions that we saw earlier. To wrap things up, this project allowed us to use tools and techniques that went beyond what we typically do in class. We worked with multiple data sets, we merged them, engineered new variables, and explored different modeling approaches, including nonlinear polynomial features and logistic regression. Creating visualizations also helped us interpret the results more clearly. Overall, this project expanded our understanding of data manipulation, modeling, and how to find meaningful patterns in health-related data.